Welcome back to the Foundry by Forge College. I'm absolutely thrilled to have you here. So we are currently right in the thick of our capstone project, building a comprehensive Solidity contract. This is all part of the Ether and Advanced State Management module within our Applied Solidity Development track. Now, if you caught our previous explainer, you'll remember we focused on framing a comprehensive deployment plan. Basically, we got our metaphorical building permit approved, and man, that feels great. But now the real physical work begins. Today's explainer is all about implementing state and storage patterns in Solidity. Because look, as any good builder knows, or honestly, anyone who's ever accidentally flooded their kitchen, you absolutely have to pour a rock-solid structural foundation before you even think about installing the plumbing. We're taking the architecture we designed and translating it directly into concrete code. Let's get into it. So here is the architectural blueprint for today's explainer. We're going to cover the architecture recap, structuring your data, storage, memory, and gas, building the state backbone, and finally verifying your state.
All right, Section 1, the architecture recap, taking it from concept to reality. Okay, so let's dive right into this golden rule of smart contract development. The foundation must be poured before the plumbing. Why is it literally so critical to implement state before you write any of your mutator functions? Well, think about what happens if you start building the functions that move Ether around first. If you haven't totally finalized your state layout, you are risking incredibly costly refactors down the line. And even worse, you invite these really subtle, nasty bugs where your storage slots or initialization semantics end up violating the core invariants of your entire contract. Functions that move or inspect Ether are completely, 100% dependent on a correct, secure state layout. State comes first, always, no exceptions. So, what exactly is going into this foundation of ours? In our capstone contract, we're building a canonical state layout that relies on three main pillars. First up, we need to track per-user deposit balances. Essentially, we need to know exactly who holds what at any given time. Second, we need a payment indexing scheme to keep a reliable historical record of transactions. And third, a permissions map for privileged actions, which is absolutely crucial for keeping our administrative functions completely secure. These are the three pillars we're going to translate into our Solidity code today. Moving right along to Section 2, structuring your data. Let's get this information organized. Okay, there are basically two fundamental ways we organize data in Solidity. First, think of structs as your custom filing cabinets. They let you group related pieces of data together, like a payments payer, payee, amount, and timestamp, all shoved into one neat, easily accessible drawer. Mappings, on the other hand, well, they're like infinite address books. They allow you to instantly connect a specific Ethereum address to a specific balance, or maybe to a Boolean whitelist to quickly check if someone has admin rights. By combining these filing cabinets and address books, we can accurately represent virtually any complex relationship in our contract. Now take a look at our engineering bill of materials here. We've got our paymentNonce for tracking unique IDs, balances to keep track of held Ether, payments to store those full struct records we just talked about, and payments by account to index everything. Notice that our starter code is intentionally using private visibility for these sensitive variables. Why do we do that? Well, by making them private, we significantly minimize the public surface area of our contract. We basically force any outside interaction to go through our specific, carefully controlled accessor functions. This enables deterministic indexing and keeps our state locked down super tight. Here's a quick stretch goal for you to ponder. When you're indexing data, like, say, linking an account to its historical payments, should you use dynamic arrays or nested mappings? This is actually a classic engineering trade-off. Arrays are way easier if you know you need to enumerate or loop through a bunch of data. But nested mappings, they are incredibly cheap for simple membership checks, like just asking, hey, is this ID in this user's list? There's really no single right answer, but understanding the nuance of that trade-off is exactly what makes you a great architect. All right, Section 3, storage, memory, and gas. Let's talk about the project economics. Before we go any further, we absolutely have to talk about S-Store. S-Store is a storage write operation on the Ethereum network. I like to call it the ultimate contractor tax. The quote-unquote Ethereum building inspectors are incredibly strict, and they will charge you exorbitant gas fees every single time you permanently write data to the blockchain. If you've got sloppy state architecture, your users are going to end up paying through the nose in gas fees. So, our primary goal here is to appease these inspectors by being as incredibly efficient as possible. So how exactly do we do that? By deeply understanding storage versus memory. Storage is the heavy, permanent vault. It's on-chain, it is very expensive, and it is strictly where our state variables live. Memory, however, is like the temporary receptionist scratchpad. It's cheap, it only lasts for the duration of the execution, and it is absolutely perfect for read-only operations. So the crucial takeaway is this. When you have an external view function that needs to return a payment struct, you should return it into memory. Copying the data out of the expensive vault and onto the cheap temporary scratchpad for an external read saves massive amounts of gas. Another real pro tip for appeasing those gas inspectors, keep your variables tightly packed. When you physically group your struct assignments together in your code, you minimize the number of separate, expensive str slots the network actually has to write to. We want our data to look like a perfectly efficiently packed shipping crate, right? Not just some disorganized pile of boxes taking up unnecessary, expensive space. Section 4, Building the State Backbone. Time for the actual construction phase. Here is our step-by-step implementation flow. First up, in our constructor, we're going to initialize the paymentNonce to 1. This is actually a really great trick. By starting at 1 instead of 0, we completely avoid zero-value collisions later on. It allows us to treat an ID of 0 as a clear, definitive indicator of an invalid or non-existent payment. Next, we add our view accessors, getBalance and getPayment, so we can securely read our data. And finally, we'll create a dedicated internal helper function called _recordPayment. Now, pay really close attention to the specific ordering of operations inside that _recordPayment helper. We call this a safe write pattern. First, you compute the ID. Second, you do a single grouped struct assignment to payments PID. Third, push the ID to both the payer and payee indexing arrays. Fourth, emit your event. And finally, increment the nonce. Following this exact specific order prevents inconsistent state, which is especially important if an external call gets introduced later on. It's just systematic, incredibly safe construction. I definitely want to highlight a really common beginner pitfall here, and it's a rule we emphasize heavily across all the learning pathways and programs here at Forge College. Never, ever attempt to return a storage pointer to a struct from an external function. Solidity simply won't let you do it the way you might think. It returns a copy from memory only in this specific context. Honestly, just like learning to wear a hard hat on a physical job site, remembering your data location rules is a completely non-negotiable safety standard for Solidity development. Section 5, Verifying your state. Time for the final building inspection. So we are going to run a basic safety inspection. And the best part is, we can do this without requiring real Ether or mainnet interaction. First, just run npx hardhat compile. You're looking for a clean zero exit status with absolutely no errors. Then, go ahead and deploy it to a local test network. Now, run your sanity checks. Verify that getBalance for the 0 address strictly equals 0. And importantly, check that getPayment1 returns an empty struct with all its fields zeroed out. Remember, in Solidity, accessing an unset mapping key shouldn't revert the transaction. It should just return default values. Seeing those defaults means your foundation is perfectly flat, level, and ready to go. So the core philosophy we've really been building towards today is this: observe state without exposing mutators prematurely. We use explicit counters, we use private mappings, and we use carefully controlled read-only view accessors. This approach keeps our sensitive state locked down tight, while still allowing us to verify that the internal logic is functioning exactly as we designed it to. And that brings us to the end of today's blueprint. Your foundation is officially poured, and your state is verified. But I want to leave you with one big, provocative question. When the actual ether starts flowing in the next phase, and all that complex business logic finally kicks in, will your state really hold up to the pressure? That is exactly what we are going to tackle in our next lesson on mutator functions. To dive much deeper into this subject, check out the full code snippets and explore tons of other Web3-related topics. I highly encourage you to visit forge.college. Keep building securely, and I'll see you in the next explainer.